Well, in the previous class, we gained an elementary understanding of the scattering of light. Today, let us go a little deeper. You see, both Rayleigh scattering and Mie scattering that we studied the last class, they are basically elastic scattering. That means the incident light neither gains energy from the scatterer nor lose energy to the scatterer. So, in Rayleigh and Mie scattering, incident light photons do not gain or lose energy to the scatterer. So, let us try to understand it more deeply. This is our scatterers, and the size of the scatterer, of course, for Rayleigh scattering, less than the wavelength of light. And let us assume our light, incident light, has two wavelengths. One is red, the other is blue. And we know that the blue light scatters 5 times more than the red light. So as this beam of light interacts with the scatterer, there will be Rayleigh scattering. So blue light that will be scattered more will be scattered as blue light only, because the photons do not neither lose energy to the scatterer nor gain energy from the scatterer. Therefore, blue light scattered as blue light only in every direction, isotropically, uniformly, all around the scatter. And red light will be scattered 5 times less than the blue light approximately, but would again be scattered as red light only, because it is elastic scattering. Blue light would have lost a lot of intensity because it underwent much higher scattering, Rayleigh scattering, and red light would rarely lose its intensity. And when here you see red light scattered light, blue scattered light outnumber. Now let us see Mie scattering. So in Mie scattering, the scatterers are much bigger in size, and essentially now the size of this is longer than the wavelength of even the red light. So it would of course be more than the wavelength of the blue light. Now the same beam of light with blue and red components, blue and consisting of two colors, red and blue, are shining. Now Mie scattering is invariant as far as wavelength is concerned. All wavelengths are scattered equally. Therefore, and again, red light is scattered as red light, blue light is scattered as blue light. Only difference is that all wavelengths are scattered equally, unlike Rayleigh scattering. So here, if you see the emerging beam, both the beams would lose equal amount of intensity because they would have undergone same scattering, same amount of scattering. Now, the incidences where photons can both gain or lose energy to the scatterer are not rare in physics and are termed inelastic scattering. A few notable examples are Raman scattering, Brillouin scattering, and Compton scattering. I must mention here that the advent of lasers has added multiple dimensions to all these effects, opening up new frontiers of physics and mind-boggling applications unthinkable had laser not existed. Let us consider the case of Raman scattering. So here again, the scatterer size is smaller, bigger than the wavelength of light. The molecules which participates in the which Raman Rayleigh scattering can also undergo Raman scattering. And let us consider an incident beam of light that is green in color. And as it interacts with the scatterer, so the scatterer molecule will have its energy levels. Let us consider two such energy levels. One is the ground energy level, another is excited. Now that we know Boltzmann distribution of population among energy levels, we know that, of course, the ground level will contain most of the molecules. And let us consider in the beginning that the excited level is practically empty. Now this light beam with photons of the energy corresponding to this green color shines it. And suppose this is the energy, and this is the energy that is required to excite molecule from the ground to the excited state. So you can see that if the photon loses this much energy, gives this much energy to this molecule, the molecule will be excited to this level. And photon, of course, would now scatter with a less energy, that is longer wavelength. But how does it happen? This does happen. How does it happen? Well, to understand that how does it happen, you actually imagine the virtual level at this position, which is away from the ground level by an energy matching the energy of the Raman photon. So you can imagine that momentarily this molecule has risen to this level, which is normally denoted as the virtual level. And then instantaneously it comes down, the molecule, excited molecule, then comes down to this level. And so essentially then the molecule stays in the excited state. So in effect, this photon gives this much energy to the molecule, and the molecule gets excited to this level. And this is scattered with reduced energy. So here it is shown as the red, red light. That means after undergoing this scattering, the green photon has now converted into red photon because its wavelength has increased. It might not have become red. It is only to suggest that the wavelength has increased because it has given some energy to the medium. This is called Stokes-Raman scattering. Let us now consider the the second case, where the excited state also has some population, although less than the ground state. That is what Boltzmann distribution will say. If you increase the temperature, then the excited state also gets populated to some extent. But the population is less than this, unless, of course, you have created population inversion. Let us not go into that. So now, once again, this Raman photon interacts with it. Now you see there are some excited species. If one of the excited species comes down to the ground state, it would release this much energy. If that energy gets added to this photon, then it will be scattered with an increased energy. That means its wavelength now will reduce instead of increasing. But in reality, how do you conceive it? How does it happen? Well, you again consider the virtual law and take this molecule from here to that level. Well, I did draw it here. This is my ground level. This is the excited level. This is the photon, Raman photon, and excited state now has some population, although less than the ground state. Now, this is the virtual level. So this photon, now this molecule which is already in the excited state absorbs this photon, climbs up to this level, which is the virtual level, momentarily. And then instantaneously it makes a transition to the ground level. So this energy, excitation energy of the molecule, now gets added to the photon. The photon now is scattered with an increased energy, which is this. So this is shown here, represented here. In this case, the green photon gets converted into blue photon. And this is called anti-Stokes-Raman scattering. Here, the photon gives its energy, receives energy from the scatterer. Now usually the excited state will be much less populated than the ground state, and therefore it is natural to expect that Stokes scattering will be the dominating process of scattering. And as the population of the excited state would be always less, therefore anti-Stokes scattering will be rare. Summarizing then, you have incident light, which is shining scatterer, and scatterer wavelength is longer than the scatterers. The scatterers are shorter size, smaller in size. The wavelength is longer. So part of the light, in fact, majority of the light, more than 90% of the light is actually Rayleigh scattering. And Rayleigh scattering, green light scatters as green light. And there will be Stokes-Raman scattering, where the photon will give part of its energy to the scatterer and excite the scatterer molecule, which is Stokes-Raman scattering. There will be anti-Stokes-Raman scattering, where the photons would gain energy from the scatterer and thus will be scattered with shorter wavelength, that is increased energy, and the my scattering will be absent here. My scattering absent. That is because the size of the scatterer is shorter than the wavelength. Wavelength is longer. For my scattering, the scatterers have to be much larger in size. Well, I think as far as scattering is concerned, we will stop here. And next, we'll study the polarization of light. Well, next is polarization of light. It is important to gain a clear insight in the polarization of light because it has very strong bearing on the emission of lasers in many ways. However, before we get into the polarization of light, I would like to tell you a little about polarized sunglasses. I'm sure many of you, in fact, most of you, must have used such glasses at one time or another, or at least know about it. In this context, I shall show you these two pictures. They clearly illustrate as to how a sunlit object would look when viewed through a polarized glass and through naked eye. This is through polarized glass. As you can clearly see, the polarizer cuts off the sun's glare. By the way, I forgot to mention that this surface of this water body has water ripples on it, and the polarizer cuts off the sun's glare originating from this water ripples. This allows a clear and unobstructed view of the river bed. The naked eye barely can see the riverbed. It's clear here. The question here is how a polarized sunglass flashes the glare of light. So now, as you know, the polarized glasses have a special ability to make the viewing unbelievable soothing by way of cutting the glare of light originating from a bright source of light or light reflected off shiny object. These are often used, as you know, while driving in the night. In the night, when you are driving, the glare of the headlight of the car which is approaching you from the opposite direction often makes it very difficult, driving very difficult, in particular if it is a very dark night with no light around, or when you are snow gazing on a bright sunny day, the sunlight reflected from the snow, white snow, milky snow, actually creates lot of obstructions, distractions of your gazing. Use of such sunglasses, polarized sunglasses, actually help you to overcome such challenges. Now, to understand the physics behind the ability of these special glasses to flash the glare of light, we need to take a closer look at the transverse nature of light wave. Light is a transverse wave. Just you may recall that when we studied Young's double slit experiment, then we have discussed about wave to some extent. So wave, as you know, basically is a sinusoidal disturbance, propagation of a sinusoidal disturbance. For example, if you throw a stone on the surface of a pond which is absolutely calm, then the stone creates a disturbance, which basically the up and down movement of the water particles. So the disturbance actually propagates in every direction, all around this point. So I can show you two directions. And this is, of course, water wave. And as you can see, the disturbance is actually perpendicular to the direction of propagation of the wave. So such waves are called transverse. So light is also a transverse wave, where of course the disturbance is perpendicular to the direction of propagation. The disturbance here basically sinusoidal oscillation of both electric and magnetic fields that are again perpendicular to each other. Light is an electromagnetic wave, and the electric and magnetic fields, they're orthogonal to each other, and the sinusoidal oscillation of this actually results in the propagation of the wave, which is of course transverse in nature. Now, suppose this is the direction of propagation, and suppose let us assume that this is your electric field at some instant, and this is the magnetic field. So their angle between them is 90 degree, and this plane in which they are oscillating, this plane is perpendicular to the direction of propagation. So it is a transverse wave. There is obviously no restriction placed on the direction in which the electric and magnetic fields can oscillate. The only restriction is that they have to be orthogonal to each other always. So if the electric field this direction, the magnetic field has to be in such a way that the angle between them remains 90 degrees. So this can rotate. Both the electric and magnetic field can rotate. There is no restriction. Only restriction is that the angle between them always have to be maintained at 90 degrees. And of course, the plane which they oscillate should be perpendicular to the direction of propagation. Three such waves have been shown here with rotating electric and magnetic field. As you can see, their angle between them is always 90 degrees, and the direction of propagation of the wave is again orthogonal to this plane on which the oscillation is occurring. A ray of light is of course made up of multiple waves. For example, now I should mention here that to always draw both electric and magnetic field makes the drawing quite complex and complicated. So we can actually choose only one of the field, either electric or magnetic field, for convenience. So let us use only electric field in all next set of drawings. It is not that magnetic field is not important. Magnetic field is just as important as the electric field, but it is only for our convenience that we'll choose the oscillation on electric field in the subsequent slides and as I move on. Now you see, a ray of light is made up of multiple waves. For example, here I have shown 1, 2, 3, 4 such waves. And say, if I consider this wave, which is the electric field oscillating. So oscillation means it is starting from zero value going up. So you see here, this is shown. This is the wave corresponding to this electric field oscillation. Electric field is oscillating from zero, slowly it is rising, then it is falling, and then it is going in the negative side, then it is again falling, and it is rising again. So this, as you know, is the wavelength of the light. So these are 4 waves I have shown here. So for a conventional source of light, each of these waves, the direction of oscillation of electric field will vary randomly because there will be many waves. So their oscillation will vary randomly. There is no correlation. Light emitted by a conventional source such as sun, therefore, has an electric field oscillating randomly in all possible directions and is called randomly polarized or unpolarized light. So for an unpolarized or randomly polarized light, the electric field will oscillate in all possible directions. Now let us see what is a polarized light and what is P and S polarization. As the name suggests, a polarized light understandably has an electric field oscillating only in a particular direction. That means as if there is only one wave which is oscillating in a particular direction. In the case of a horizontally polarized light, denoted normally as P polarization, oscillation of the electric field always occurs on a horizontal plane. As you can see, the electric field is always oscillating in a horizontal plane and it doesn't rotate in any other direction. The oscillation plane is always horizontal. So a vertical polarized light, which is denoted by S polarization, the oscillation of the electric field, on the other hand, will stay confined on a vertical plane, as you can see here. The oscillation of the electric field is now occurring on a vertical plane, and it stays in this plane. This is a vertically polarized light and is denoted as S polarization. Well, I end for now here and begin our next class right from here.